Hello students, in previous lecture we have studied about the different types of work done takes place in different types of processes. That is, PV type of work done takes place in isothermal and irreversible process, and maximum work done which is takes place in isothermal and reversible process. And the derivation for Wmax we have already studied or learnt in the previous lecture. Today we are going to discuss on the new concept, that is enthalpy and enthalpy of the system. Then what is enthalpy? Enthalpy is nothing but it is a one of the type of energy which is related with the substance. Isn't it? All of you studied about the internal energy. Internal energy which is denoted by U. U is the internal energy of the substance. Here we will discuss about the enthalpy of the substance as well as enthalpy of the system or enthalpy of the chemical reaction. Then first of all, see here, what is enthalpy? Enthalpy is denoted by that capital H, and it is nothing but enthalpy of any substance. It can be calculated using this formula, that is H is equals to U plus PV. That means, see here, H is the enthalpy of that substance, U internal energy of the substance, and PV type of energy, PV type of energy which is related with that substance. Then enthalpy is nothing but it is a sum of internal energy of that substance and PV type of energy of that substance. Then here we will consider about the enthalpy of the system. Then enthalpy of system which is denoted by, that is delta H. That means it is a change in enthalpy of system. And see here, in the system, when system is at initial state, then when it is at initial state, then it has its internal energy, that is U1, as well as it has PV type of energy. That means here PV type of energy, that is P1 V1 type of energy which is related with that system when it is at initial state. When system goes to final state, that is B, through any process, it converted from A state to B state, and when it reaches to final state, then U2 is a internal energy of system when it reaches to final state or it reaches to the state B. Then here P2 V2 type of energy which is related with that system. If here when system is at A state, then enthalpy of that system is H1, and when system reaches to B state, then enthalpy of that system is H2. Then enthalpy of that system or enthalpy of that process or enthalpy of the chemical reaction which takes place in this system can be calculated that by delta H is equals to H2 minus H1. But here according to this formula we can calculate the H2 and H1. That is, see here, when system is at initial state, then H1 can be written like that, U1 plus P1 V1. Let this equation number 1. Then when system reaches to final state, then H2 is the enthalpy of that system when it reaches to final state. That means H1 is a enthalpy of system at initial state, and H2 is a enthalpy of system when system reaches at final state, and therefore here we can write the enthalpies at initial state as well as at final state of the system. That is, here H1 is equals to U1 plus P1 V1. Let this equation number 1. H2 is U2 plus P2 V2. Let this equation number 2. Then here we can calculate enthalpy change of system, or the process which takes place in the system. That is, here delta H is equals to H2 minus H1. Then putting the values of H2 and H1, then from equation 1 and 2 we can write delta H is equals to, that is, H2 minus H1, whereas H2 is U2 plus P2 V2 minus H1 is U1 plus P1 V1, and therefore delta H is equals to, simplifying this equation, U2 minus U1 plus P2 V2 minus P1 V1, and therefore delta H is equals to delta U plus delta PV. And here, if process takes place in the system which is isobaric process, that means here P1 is equals to P2 is equals to P, that is P is constant. That means P1 and P2 are equal, and here in isobaric process pressure is constant, and that is Pex is equals to P, which is constant. Therefore here we can write delta H is equals to delta U plus, see here, as P is constant, therefore P delta V, and that is the equation for changing enthalpy of the system. And here all of you studied about one more equation, that is QP is equals to delta U plus Pex delta V, and that is the mathematical expression which is obtained by applying first law of thermodynamics to the isobaric process. Then let this equation number 3 and equation number 4, then from equation number 3 and equation number 4 we can conclude that delta H is equals to QP. That means here delta H, which is nothing but it is a change in enthalpy of the system, is nothing but it is a heat transferred to the system, or heat transferred from the system at constant pressure. That QP is nothing but it is a heat transferred, heat exchange takes place between system and surrounding when pressure is constant, and that is the change in enthalpy of the system. And see here, as Q is a state function. Therefore, here enthalpy is also state function. That means here enthalpy and Q are the state function. State function, that means those are the properties which is depends upon state of the system and not on the path followed by the system. That means enthalpy or heat transfer between system and surrounding or heat exchange during the process takes place in the system is also state function, because values of those physical quantities, that is of enthalpy and heat transfer or heat exchange between system and surrounding, which is depends upon state of the system, and therefore enthalpy and heat transfer, that is Q, are the state function. Enthalpy change of the system, that is delta H is equals to delta U plus P delta V. That is the mathematical expression for enthalpy of the system that we got here. Then we will study about the relationship between delta H and delta U. That is, here delta H is enthalpy of the system and delta U, that is the change in internal energy of the system. Then what is the relationship between enthalpy of the system and change in internal energy of the system? Then see here, suppose in the system, if there is a reaction or the process which is involved in the system, that there are reactants and products which are involved in this process if they are in solid state. Then see here, the solid substance which are non-compressible. That means, see here, if we give the pressure on it, then no change in volume takes place here, or those solid substances which cannot be expanded. That means no change in volume in the solid substances. Then there is no change in the volume. That means here delta V is equals to 0 for reactions involved for solid state substances, and here as well as if the reactions which is takes place or in the system for liquid substances. Liquids are also less compressible or non-compressible. Therefore, then delta V is negligible for liquid state, and therefore the reactions which are involved, which is related with solid or liquid type of substances, then delta V is negligible or delta V is 0. Therefore here delta H, that means enthalpy of the system or enthalpy of the reactions which is related with the solid or liquid type of substances, delta H is equals to here delta U plus P delta V. But here for those type of reactions that involve for solid and liquid type of substances which takes place in the system, delta V is 0. Therefore here delta H is equals to delta U, because P delta V it becomes 0. That means here enthalpy change for the reaction takes place in the system for liquid and solid is nothing but it is the change in internal energy of that substances. That means here no work done takes place for the reactions of solid and liquid type of substances which takes place in the system. Then one more condition, that is if here the reactions which is takes place and the substances which is involved in this process is of gaseous substances. If here the reaction which is related with the gaseous reactants and gaseous products, and then here gaseous substances are compressible or those are highly compressible, and here therefore there is change in the volume of gaseous substances takes place during the process which is takes place in the system. Then let us consider V1 is the volume of gaseous reactant when system is at initial state, and V2 is the volume of gaseous product when system at final state. And here suppose N1 are the number of moles of reactant molecules. That means when system is at initial state, and when system reaches to final state, products are there. Therefore N2 are the number of moles of product when system reaches to final state. And then we can get the relationship between delta H and delta U for the reactions of gaseous substances. That is, see here, delta H is equals to delta U plus P delta V. But see here, there are change in volume of gaseous substances takes place in the system. Therefore here we can write that delta H is equals to delta U plus P, that is delta V, V2 minus V1. And here we get the equation, that is delta H is equals to delta U plus P V2 minus P V1. But here suppose the gaseous reactant molecules and the products, if that gaseous substances, then reactant and products which are gaseous, that are ideal gases, then according to general gas equation, for reactant molecules when system is at initial state, we get the equation, or that PV is equals to nRT, which is converted into PV1 is equals to N1RT at constant pressure and constant temperature. Similarly, for gaseous product at final state, then system when reaches at final state, then products are there. Therefore that equation, that is general gas equation, it becomes PV2 is equals to N2RT. Then see here, we can put the values of PV1 and PV2 in equation, that delta H is equals to delta U plus PV2 minus PV1. Therefore, here delta H is equals to delta U plus that PV2, that is N2 RT, minus PV1, that is N1 RT, and therefore this equation becomes delta H is equals to delta U plus, see here, RT, which are common. R is a gas constant, T is a constant temperature. Therefore, here N2 minus N1 in bracket, that is RT, which is common, which is taken outside the bracket, and therefore delta H is equals to delta U plus N2 minus N1, that is N2, that are number of moles of product at final state, and N1 is the number of moles of reactant molecules when system is at initial state, and therefore that is the change in the number of moles of reactants and products. Therefore that is written like that, delta N RT. That is the one more mathematical expression for changing enthalpy for gaseous type of reactions involved in the system. Then we will discuss about the work done takes place in chemical reactions, and the sign conventions which is related with that work done takes place in the different types of chemical reactions. See here, all of you studied about that. W is equals to minus PEX delta V, that is for isothermal and irreversible process when P is constant, that is pressure remains constant. That when P remains constant, PEX is a P. Therefore that equation becomes W is equals to minus P delta V. Therefore here W is equals to minus P, that is delta V means V2 minus V1, that means volume at final state of the system or volume of the product when system reaches to final state, and V1 is the volume of reactant molecules when system is at initial state, and therefore here W is equals to minus PV2 minus into minus V1, that is plus PV1. Therefore here W is equals to minus, see here, taking minus is a common, and therefore PV2 minus PV1, and see here, putting the value of PV2 minus PV1 here, that is here PV2 is N2 RT minus PV1, that is N1 RT, and therefore W is equals to minus N2 RT minus N1 RT, that is delta N RT. That is the work done takes place in chemical reactions in which gaseous substances are involved in it. Then the sign convention for work done. See here, sign conventions sign convention for W. Then see here, W is equals to minus delta nRT, and here that sign of W, which is depends upon the value of N1 and N2. Then see here, there are three conditions involved in gaseous type of reactions which is takes place in the system. If N2 is greater than N1, that means number of moles of products are greater than number of moles of reactant molecules. That means see here, at initial N1 moles are there, and when system reaches to final state, the number of moles of product, that is N2, which is greater. Therefore here piston moves upward. That means because here number of moles of product which is greater than the number of moles of gaseous reactant, therefore here volume of the system increases. Therefore here delta N, as N2 is greater than N1, therefore delta N is positive. Putting the value of that delta N, which is positive, in this equation, therefore here the value of W, which becomes negative. Therefore W is negative. That means work done is negative. That means here, as work done is negative, therefore here work done takes place by the system, and therefore here work done which is takes place in this system, that is negative. That means here W is less than 0. In second condition, if N2 is less than N1, then see here the volume of system decreases, and therefore here compression takes place and piston moves downward. Here therefore volume of the system decreases and number of moles of product decreases than the number of moles of reactant. Therefore here delta N, that is N2 minus N1, here N2 is less than N1, therefore delta N, which is negative, and as here delta N is negative, W is equals to minus delta nRT. Then putting the value of that delta N, which is negative, minus minus becomes positive. Therefore here the value of work done, it becomes positive, and therefore here as work done takes place which is positive, therefore here work done takes place on the system, and that means here the sign of W, which is depends upon number of moles of reactant and product. Then there is one more condition, if N1 is equals to N2, then delta N, that is 0. That means no change in the number of moles of gaseous reactant and product molecules during the process takes place in the system, and therefore here W is equals to 0. That means here work done which is takes place in the system is 0. That means here no work done takes place in the system. That means here the value of W, which is depends upon, or sign of that work done, which is also depends upon number of moles of gaseous reactant and products which is involved in the reactions takes place in the system. That is about the enthalpy and enthalpy change of the system. In next lecture we will study about the enthalpy changes, which is related with different types of physical transformation processes. Thank you.